With the great strides in technological development, new and better products are being mass-produced to make our lives more pleasant and provide more variety. It is, therefore, very natural for us to desire goods which satisfy our needs and to demand quality at a reasonable cost. This way of thinking or attitude of the consumer is taken into consideration by the enterprise that is producing the goods. When a new product is to be manufactured, be it an ordinary consumer product or an industrial product, it should be developed and produced so as to meet the customer's desires. And the desired quality should be determined accordingly and built into the product. Now, what should the manufacturing department do to ensure that the desired quality is built into the product? A skilled worker often depends on his own experience, intuition, and determination, and takes sporadic action to solve quality problems. Although this approach has contributed to solving many quality problems so far, it is no longer effective for products of this modern age, because the situation now demands speedy action in the face of increasing competition. So, let us now listen to what Dr. Kaoru Ishikawa has to say on the subject, based on his extensive international experience in the field of quality control.
Quality of products and quality control in Japan have progressed remarkably, particularly during the last 3 decades, through the continuous effort of top management, quality control engineers, quality control circle leaders and members. All of them studied and practiced with enthusiasm simple quality control techniques.
The appropriate method for speedy and effective quality problem solving is to analyze quality problems by investigating the causes of chronic defects in each main quality characteristic based upon factual data. The first prerequisite for this approach is the collection of appropriate data. The need for collecting such data cannot be overemphasized, as this is the scientific approach to solving problems in any field whatsoever. Once problems are identified, the question is whether to use past records or collect data afresh, and then we must examine how to collect appropriate data and proceed with collecting such data for analysis. Various past records should be studied and tested for their validity before they are selected for analysis. The measures to be taken for problem solving should be based on correct and valid data. It goes without saying that a correct solution will not come out of incorrect data. When the data available is not sufficient or proper, correct data should be gathered afresh in a systematic way. Now, what is incorrect data? Let us pause and think about it. An example of this is feigned data, which is caused by not recording defectives just as they occur, in an attempt, for example, to show a smaller percentage of defectives than had actually occurred, as you can see on this chart. Incorrect data can also be caused by large measurement errors when the measuring instrument is out of order or when the operator is ill-trained. Here we can see the difference caused by reading the scale at an angle. Certain quality characteristics cannot be measured without destruction. Therefore, we must take samples of the product for measurement. But the question is, how should the sampling be done? Sampling errors can arise when the method of sampling is not accurate but is biased, merely for the sake of easy sampling. Care should be taken to avoid sampling only from seemingly good portions of a lot or from those selected consciously or unconsciously. All sampling should be done at random. Here we see a box from which samples have been taken at random. How can we sample at random products that are stocked or stored, as you can see in this picture? Random sampling cannot be conducted once products are stored in a warehouse or packed in a box. It should be done before they are stored or packaged. Random sampling is also impossible for products such as textiles, steel wire, and so on, which are processed continuously. A method similar to that of random sampling should be devised for such products. Now, there are 7 basic tools by which many quality problems could be identified and solved. These may be likened to the 7 tools, let's say, which were at one time indispensable to a lady, such as a pair of scissors, knife, needle, spool, ear pick, hair tweezers, and nail clipper. These 7 tools, perhaps we can call them weapons in our combat for ensuring quality, are, as you can see on the screen: check sheet, histogram, Pareto diagram, cause and effect diagram, stratification, scatter diagram, graph and control chart. Now let us listen to what Dr. Kano has to say about the 7 tools, based on his many experiences in Japan and other Asian countries.
Perhaps there may be some who tend to disregard the 7 tools in favor of the more sophisticated techniques, as each of the 7 tools looks so simple and easy. But this is not correct, because if you combine these simple tools effectively, most of the quality problems in the plant can be solved.
Let us get back to the 7 tools enumerated earlier. Their functions are to A. Detect problems, B. Narrow problem area, C. Assess factors which seem to cause the problem, D. Determine whether the assumed causes of defects are true or not, E. Prevent errors due to omission, haste, or carelessness, F. Confirm the effects of improvement, G. Detect outliers. Let us now take a look at each of the 7 tools which involve the collection of various types of statistical data. First of all is the check sheet, which is a handy tool to classify data by simply putting in check marks on the readings made instead of writing them down. For this purpose, a form in which all necessary items are printed is used. The more important purposes of check sheets are to survey process distribution, defective items, locations of defects, causes of defects, etc. Now, would your workers enjoy collecting masses of statistical data and recording them for analyses? The check sheet, by facilitating entry of information, will overcome such a problem, as we shall see in the following frames. Let us consider the case of the component you see in this frame. It is necessary to investigate its quality characteristics by taking measurements on several samples. This is a check sheet for analyzing the measurements taken. All that is required is to insert check marks, as you will see now. Here is the completed form with check marks indicated against a particular dimension shown at the top of the table. The advantage of this check sheet is that it is not necessary to record each measurement separately and then sort out the readings in order to study the distribution. From this check sheet, the distribution of measurements is quite clear. You now see a form of a check sheet for studying the types of defects occurring in a plastic forming plant. The check marks appearing in a horizontal line indicate the number of defects of a particular type. Whenever a worker on the injection molding line observed a certain defect, all he had to do was to make a check mark in the appropriate line. Thus, at the end of the day, one could immediately see the numbers and types of defects that had occurred. Here is another type of check sheet where the locations of defects in the production of laminated automobile windshields are marked on the sketch of the windshield. Whenever the worker saw a bubble in the glass, he marked the location and form on the check sheet. After several such investigations, it was found that most of the bubbles were on the right side, from which it was inferred that the right side was receiving less pressure during the laminating process. Let us next consider the second tool, namely the histogram. A histogram is basically a graphical presentation of a series of measurements grouped into convenient classes or intervals for the purpose of grasping the shape of the distribution of the measurements. Let us now see how a histogram is compiled. Here is a series of 100 measurements of the thickness of metal blocks which are components of an optical instrument. Now, by looking at these figures, can you judge the variation in measurements or tell something about their distribution? It is really very difficult to do so by this table alone. Therefore, it is necessary to devise some form for arranging the data. Now, let us look at the completed histogram based on the above data. What can you infer from this? Is the picture clearer? Let us now proceed to compile this histogram. We first have to find the maximum and minimum of all readings and hence the range of the observations. Here in this frame, the maximum and minimum readings in each horizontal line are indicated. Here you see the same chart with the maximum and minimum readings, XL and XS, from each line shown on the right-hand side. From the columns on the right-hand side, we now find out the maximum and minimum of all readings, namely 3.68 and 3.30. The next step is to divide the range between 3.68 and 3.30 into about 10 classes so that the mid-values of each class are round numbers. In this particular case, you can see that there are 9 classes with the class boundaries and mid-values shown on the screen. This leads us to the frequency table shown here, where the tally of measurements in each class is indicated by check marks together with the frequency of occurrences shown on the extreme right. Now, in order to make this representation more vivid, we construct the histogram, which you now see on the screen. Here, the frequency of occurrence of measurement in each class is represented vertically against the mid-value of the classes shown horizontally. The lower and upper specification limits are also shown, those sections of the histogram which are outside these limits being shaded. The histogram reveals what is known as the dispersion in the measurements. Let us now look at a few types of histograms. The shape of a histogram can reveal useful information on what should be looked into for solving quality problems. Now, look at this histogram compiled from the measurements of parts delivered by a subcontractor. This histogram has a cliff-like appearance on the left, which was possibly caused by the contractor rejecting all those that fell below certain measurements by inspection. Obviously, the manufacturing process was out of control. In this histogram showing the load characteristics of a microswitch, it will be seen that the average value is inclined towards the upper specification limit and that the dispersion is broad. Armed with this information, the problem were analyzed through control charts and other methods, resulting in a reduction in the number of defectives. Now, let us look at another histogram. Here is one drawn for the hardness tests carried out on sheet metal panels supplied to an electrical machinery manufacturer. Since the dispersion was broad, investigations were made and it was discovered that the parent company was purchasing sheets from 2 suppliers. Upon separately testing the sheets from the 2 suppliers, the stratified histogram, which you now see, were drawn. By drawing 2 separate histograms, the differences in hardness in the sheets supplied by the 2 suppliers were quickly revealed. This is a case of stratification, which will be discussed later in the program. We now come to the third tool, namely the Pareto diagram. This is based on the well-known Pareto principle. Before explaining the application of the Pareto diagram, let us look at the following scene at a plant.
There are several defects which have all been listed, and there are too many, and I don't know how and where to start remedial action.
Yes, but you should be able to judge correctly and take necessary action with all your experience.
Yes, but how does one get about it? I'm completely at a loss and don't know what to do.
Well, I think this is a case where you could easily draw a Pareto diagram and then identify which of the defects should be tackled first. In effect, a Pareto diagram is a tool for isolating the vital few from the trivial many. I shall now show you how to construct a Pareto diagram and how you could use it to isolate the vital few defects.
Now, look at this chart which shows the number of defects in manufactured products classified according to the types of defect. This shows the major types of defects, but by plotting the diagram, as you see now, representing the number of defects vertically against the types of defects horizontally, the picture becomes a little clearer. Next, by drawing a cumulative curve as we see here, the diagram is complete. It is clear from this that caulking and connecting account for about 75% of the total defects. Therefore, it is these two items that should be tackled first. Experience shows that it requires the same effort to reduce a tall bar as to reduce a very short bar by the same proportion. But if we can reduce the tallest bar shown in the figure by half, our accomplishment will be considerable and far outweigh the effects of completely eliminating the shortest bar. The importance of the Pareto diagram is that it tells which factors are most important and deserve our constant attention. Now, let us take a look at the two charts on the screen. The left-hand chart is a Pareto diagram before improvement showing that improper rotation was the major type of defect. Having remedied this defect, we now construct a Pareto diagram after improvement as shown on the right-hand side. Here, the tallest bar has reduced considerably, and it now occupies second place in order of importance in respect of defects. The overall effect of improvement is shown by the arrow on the right. Now, let us look at another example of the Pareto diagram. Here is one that was used to improve machine breakdown prevention and preventive maintenance planning. The horizontal scale indicates the locations of trouble spots. On the basis of this diagram, the goal for improvement should be the oil pressure line. Pareto diagrams can also be used for improving safety in the plant. In the Pareto diagram, you can now see most of the injuries related to the fingers. With this information, the various causes of finger injuries were analyzed and appropriate measures were taken. To sum up, the Pareto diagram is an indispensable tool for knowing exactly the target to be chosen for concentrating efforts towards improvement. We can, in fact, say that the Pareto diagram is one of the first steps towards making improvements. Let us next take up the cause and effect diagram, which is a useful tool for solving quality problems and is now widely used throughout the world. Now, let us look at how a cause and effect diagram can be constructed. Consider, for example, the cooking of special rice and study the taste of rice as the quality characteristic that we are desiring to improve. First, indicate the quality characteristic, namely the taste of rice, and draw a bold arrow from left to right as shown. Next, indicate the main independent factors affecting the taste of rice and draw arrows leading to the first bold arrow. Usually, the sub-processes are used as the main independent factors, as is shown here. Next, indicate the sub-factors which can cause a change in quality of each of these 5 factors shown in the previous frame, and draw arrows leading to the earlier 5 arrows. In this manner, we proceed to indicate the sub-factors affecting the main factors, and draw the complete diagram as shown on the screen. The cause and effect diagram is sometimes referred to as the fishbone chart due to its resemblance to the skeleton of a fish, as you can now see. Here is an example of a cause and effect diagram where machine trouble is traced to the main causes, namely workers, materials, inspection and tools, and then analyzed further to the sub-causes and so forth. Cause and effect diagrams can sometimes look very complicated, as is shown here. Now, this is an example of a bad cause and effect diagram where the person who constructed the diagram had not looked sufficiently in depth into the various causes. This is like a fish with merely bone and no meat. Now, let us look at the relationship between the Pareto diagram discussed earlier and the cause and effect diagram. Once again, you now see the Pareto diagram for the defects in a manufactured product, classified according to the types of defects. Here, drawing the cause and effect diagram together with the Pareto diagram, we at once see the relationship. In other words, we have now to draw a fresh cause and effect diagram for caulking, as it is this cause which we must now reduce. In drawing a cause and effect diagram, brainstorming plays an important part in cause and effect analysis. Each participant in a brainstorming session is encouraged to suggest whatever ideas he likes. Criticism of any idea is banned during brainstorming. The leader of a brainstorming session should take up and list any ideas suggested, no matter how trivial they may be. He can adjust or disregard them later if they are found to be inappropriate. The cause and effect diagram should be plotted so as to reflect the opinions held by all the personnel concerned, such as foremen, operators, as well as engineers. In particular, the ideas suggested by shop personnel can be significant because it is they who know the actual operations on the shop floor. Also, it is necessary to foster a spirit of teamwork to solve quality problems by the organized efforts of all personnel. The engineer or superior is often preoccupied with his principles and insists that things ought to be just as he reasons. It is important to consider the opinions of those who know the facts firsthand. Sometimes even a third party may have to be consulted. Before leaving the subject of cause and effect diagrams, let us look at the diagram shown on the screen. Here, the causes of distortion on the side column were analyzed, and it was suspected that machine capability was the principal cause of distortion. Looking further into the matter, it was traced to an individual machine out of a group of machines. In other words, the cause was classified, or shall we say stratified, to one particular machine. This brings us to the fifth tool for problem solution, which is called stratification or classification of data collected on a quality characteristic. All data must be stratified according to individual operators, by specific machines, and so on, in order to make sure of the significance of the assumed factors. To explain this principle, let us look at a simple example of this beaker where sand, stones, and water are thoroughly mixed. Upon leaving the beaker to settle, you observe that after some time, the stones, sand, mud, and water would separate out, as you can now see on the screen. In other words, stratification has taken place. This principle is used to stratify the causes of defects in manufacture, as the following example will reveal. Consider the case of two machines, A and B, each having produced 50 units of the same product. All the units produced were then mixed and 100% inspected. As a result, 50 units were rejected. This means that the product was 50% defective. The cause of the above high rate of defectives was investigated by stratification or by classifying the production data by the two machines. The investigation revealed that the 50 units produced by machine A had all been rejected and the remaining 50 by machine B accepted. Thus, the cause was assigned, which could not have been done if the data had not been classified by machine. Troubleshooting is difficult if data is not classified according to materials used, machines employed, by whom, when, etc. If data is classified lot by lot, historically and by factors, it would be easy to assign and remove the causes of trouble, if any, in a process. This frame shows lot-by-lot inspection on the performance of tape recorders. Effective criteria for stratification are A. Type of defect, B. Cause of defect, C. Location of defect, D. Material, product, date of production, working group, individual operator, parts supplier, lot, etc. This brings us to the sixth of the tools to be discussed in this program, namely the scatter diagram. The scatter diagram is one of the simplest and most effective ways of presenting graphically a trend or relationship between two variable factors. While stratification verifies the effects of assumed discrete causes on the quality characteristic, the scatter diagram verifies the effects of assumed continuous causes on the quality characteristic. In addition, scatter diagrams serve to show up the relationship between one cause and other causes, or one effect and other effects. Now, let us look at the case of a fiber plant where there was a problem of elongation in fiber. Assuming that the moisture content was a possible cause, this was investigated by drawing a scatter diagram plotting elongation against moisture content, and the result was as you see in the frame, which indicated that the greater the moisture content, the larger was the elongation. Therefore, to control elongation, we must control moisture content. Now, look at the scatter diagram obtained by plotting Brinell hardness number against tensile strength. Based on readings taken on different samples of a certain kind of steel, the objective was to see if there was a relationship between tensile strength and hardness number. Because, since the tensile strength test is destructive, it would be more economical to use the non-destructive hardness number test if there was a definite relationship. This is one of the more important uses of the scatter diagram. Here we see two scatter diagrams, the one on the left showing a definite positive correlation between X and Y, and the one on the right indicating a trend in a positive correlation. In a similar manner, you can now see two scatter diagrams, one with a definite negative correlation and the other indicating that a negative correlation may be present. Now, in the case of this scatter diagram, it is clear that no correlation can be established. We now come to the last of the 7 tools, namely graph and control chart. These, which will form the subject of a separate film strip in the series, will not be discussed in detail, but just briefly touched upon. A graph can be of the bar type, broken line type, circle type, etc. The histogram and Pareto diagram are examples of the bar type. The broken line type is often used to show dynamic changes. The circle type is also known as a pie chart. One of the specific types of the broken line chart is the control chart, which provides information on the state of a process, namely whether the process is stable or not. Here is an example of a control chart where the measurements are plotted against time, from which it is clear how the measurements are with respect to the upper and lower control limits of the process. The points outside the control limits show that the process is out of control. Control charts will form the subject of another program and will, therefore, not be discussed here. We have just discussed 7 important tools for locating and solving problems in quality. You will see them summarized on the screen in order to refresh your memory. Let us once again hear what Dr. Kano has to say on this subject.
If you wish to derive benefits from the 7 tools, I recommend that you actually apply them to solving problems in your plant. After all, practice makes perfect.
So let us now take a case where the tools discussed earlier will be applied to an actual situation. Here is a case of a factory producing silicon transistors, the manufacturing process for which you see diagrammatically on the screen. The problem faced was the low yield of the A-type transistor. The first tool to be applied was the Pareto diagram, which you now see and which revealed that the major defect to be investigated related to the thickness of the wafers. Next, a graph was drawn showing the percentage of defects in respect to wafer thickness over a period of 1 month. It is clear from the graph that this defect is chronic as the high percentage is continuing. Therefore, further detailed data should be collected. Next, data was collected by sampling 3 slices of wafers daily for 8 days. The thicknesses of the wafer being measured at 5 points of every sample slice as shown. Here you see an extract of the recorded data in tabular form. Using this information, this histogram showing the wafer thickness after etching was constructed indicated those thicknesses lying outside the lower and upper specification limits. Now, to find out whether the dispersion in thickness after etching occurred in the manufacture of the wafer itself or in the etching process, a scatter diagram was drawn. As you can see on the screen, there is a strong correlation between wafer thickness after etching and etching quantity. Thus, it was concluded that the etching process itself was causing the dispersion in wafer thickness. Next, the plant personnel discussed the reasons why etching produced so much dispersion. They then got the idea to investigate the different measurement points on the wafer and produce stratified histograms for the 5 points. You can now easily see the difference in average thickness measured at the 5 different points. Next, a cause and effect diagram was drawn with the average difference of etching quality among the points as the effect. As a result of active discussion by all concerned, the principal cause was traced to maladjustment of a jig which was used to fix the wafer in the etching bath. The jig was, therefore, examined and corrected, and in order to confirm the effects of improvement, a histogram of wafer thickness after etching was now constructed. Here you see that the thickness all lie within the specification limits. Finally, in order to ensure that the corrected state was maintained, appropriate measures were taken as you see enumerated in this frame. We have just seen a very simple case of how some of the tools described earlier could be applied to solve quality problems. It should be borne in mind that all the tools at our disposal should be considered and applied, noting their interrelationships. However, tools alone are insufficient, and in any problem-solving activity, the ideas, opinions, skills, and cooperation of all persons concerned should be continually employed, since quality problem solving is not an individual effort, but really a group effort. Before we conclude this program, let us once again hear what Dr. Ishikawa has to say.
Remember always that the objective is not merely to use the various tools, but to solve the problem with which we are faced, rather than the adoption of sophisticated techniques. The use of simple technique by as many people concerned can be more effective, particularly at the introductory stage of problem solving. Above all, quality control requires sound judgment and proper action based upon factual data collected in the shop. Quality cannot be achieved merely by the desk calculations, but rather by the activities in the plant based on the desk calculations.
It is hoped that the program would shed some light on the principles to be observed in dealing with quality problems. Let quality be our watchword by which more and more products of better quality will be produced to make our lives pleasant and enjoyable.